The learning objectives of this chapter are to identify the major hazards associated with entry into an enclosed or confined space, to examine oxygen deficiency and toxicity in greater detail, to recognize the origins of some of the vapors that may be present in an enclosed or confined space, and to understand the reasons behind some of the additional risks that may be present in an enclosed or confined space entry situation. Identification of the hazards is a part of the risk assessment that must take place prior to any potentially hazardous task on board. The risk assessment should seek to establish the hazards that are or will be present at the work location, and then identify the significant risks arising out of the activity. For each potential danger, the competent person must assess the likelihood of its occurrence and the severity of harm, should it occur. Those at risk should be identified, as should the way in which they are at risk. A calculated judgment of whether the risk is tolerable is required. Consideration should be given to the effectiveness of existing controls and whether they need modifying or supplementing. The principal hazard associated with an enclosed or confined space, as we have already established, is the atmosphere inside. We will first examine various elements that may be present within that atmosphere, and the specific hazards that they present to anyone entering the space. Then look at additional hazards that may have a significant bearing on the task to be carried out. If an empty tank or other enclosed or confined space has been closed and unventilated for some time, the internal atmosphere may have become unsafe, because it then contains insufficient oxygen, or has become contaminated, or both. This may be due to a number of reasons, including corrosion, that is, rusting or other oxidizing processes that deplete the oxygen content of the atmosphere may have occurred, particularly if small amounts of water have been left lying in the space. Oxygen-absorbing chemicals may have been present. Oxygen-absorbing cargoes may have been carried. Gases from volatile cargoes may have displaced the oxygen in the tank. Stored items, which are unsealed or have leaked, may have contaminated the atmosphere. Hydrogen may have been produced in a cathodically protected cargo tank used for ballast. Oxygen may have been displaced by the use of carbon dioxide or other fire-extinguishing agent. Inert gas may have been introduced into the space. Crude oil carriers, product tankers, and oboes all carry oil as cargo. All power-driven vessels have oil in their fuel tanks. The possibility of exposure to hydrocarbon vapors therefore exists on all ships. Click on the labels for more information. Hydrocarbon gases are flammable as well as toxic, and may be present in fuel, cargo, or slop tanks, which have contained crude oil or its products. Hydrocarbon gases or vapors may also be present in pump rooms and cofferdams, duct keels, or other spaces adjacent to fuel, cargo, and slop tanks, in the event of leakage between the compartments or from equipment in those spaces. Certain components within the vapor of some oil cargoes, such as benzene and hydrogen sulfide, are particularly toxic. Mercaptans, or organic compounds containing sulfur, are found in some crude oils. Some components are also carcinogenic, that is, cancer-generating. Great care must be taken to avoid exposing personnel to these risks. It is not just oil, however, that presents a toxicity risk. Other vessels may be similarly exposed due to the nature of their trade. Click on the labels for more information. Many cargoes carried in chemical tankers or gas carriers are also toxic. Personnel must always consult the safety information for the cargoes being carried. Chemicals are sometimes carried in drums in general cargo vessels and also in containers. There is a possibility of leakage if these have been mishandled or improperly stowed, or due to heavy weather. Both treated and untreated timber generate carbon monoxide, as do fruit and vegetable cargoes. Trace components of inert gas, such as carbon monoxide, sulfur dioxide, nitric oxide, and nitrogen dioxide, are toxic. Vegetable, fish, and animal oils interact in a hazardous manner with seawater, which may lead to the release of toxic hydrogen sulfide. Particular care must be taken where residues of such products remain in tanks that have been washed with seawater. Hydrogen sulfide or other toxic gases may also be generated where grain or similar residues choke up bilge systems in bulk cargo carriers, or become wet and begin to decompose. Coal or swarf will readily consume oxygen in a closed hold, and bulk sulfur will generate its own poisonous fumes. Sewage reacts with salt water in a similar way, and toxic hydrogen sulfide may again be released if the two are mixed. Special care must be taken when washing out waste storage tanks prior to entry. There is also a risk of bacterial infection from waste. Spaces should be cleaned before entry, and any residues washed away and ejected, avoiding skin contact, before any other work is commenced. Appropriate protective clothing should be worn. Flammable vapours may still be present in cargo or other tanks that have contained oil products or chemical or gas cargoes. Pump rooms and cofferdams, duct keels and other void spaces adjacent to cargo, fuel and slop tanks may also contain flammable vapours in the event of leakage between the compartments or from equipment in those spaces. Vapours are not the only source of danger to personnel entering an enclosed space. Residues from previous cargoes can be hazardous on contact with the skin or eyes, or may affect the condition of the tank by, for example, making the decks and ladders slippery. Click on the labels for more information. In addition to inhalation or breathing in the fumes, liquid chemicals can be hazardous in other ways through ingestion or swallowing the liquid, skin contact, causing irritation or possibly burns, or absorption, that is, penetration through the skin. The degree of damage to living tissue, internal organs, or the central nervous system depends on a number of factors, including the inherent properties of the product, the concentration, and the amount of exposure, both in terms of time and area exposed. Some products produce asphyxia or loss of consciousness through lack of oxygen. Others have an anesthetic effect, that is, loss of consciousness due to their effect on the nervous system. Certain products burn, while others freeze, producing frostbite-like effects. The actual access into the space, such as a ladder down into a tank, may be quite hazardous under normal conditions, but the risks will usually be increased if the ladder rungs and handrails are slippery or the personnel entering have to wear bulky breathing apparatus. A fall from a ladder is likely to result in serious injury, and movement should therefore be steady and controlled, with a firm grip retained at all times. Entry into an enclosed or confined space may be for an inspection or maintenance and repair. Maintenance and repair tasks such as cleaning, recoating or welding will all introduce additional hazards of their own, including cleaning may disturb hazardous residues, releasing potentially dangerous fumes. Coating material will certainly emit fumes, and, depending on the area to be covered, extra mechanical ventilation or even an artificial air supply will need to be provided. Hot work carries a particular set of risks and will require additional risk assessment and work permits to be completed. Tests will need to be made for flammable vapor. There is a possibility that a hazard may transfer from another space, either through a crack to an adjacent space or through valves and piping. Great care must be taken, so far as possible, to isolate the enclosed space. The risk assessment must identify any potential hazards that may migrate to the enclosed space in question and ensure that all possible precautions are taken to protect those inside. If the space to be entered is adjacent to a cargo or ballast tank, or involves work on or near sea valves, or is below the waterline, particular attention should be paid to the risk of engulfment, whereby those inside the space could be overcome by a powerful inrush of water or other liquid before having the chance to escape. In addition to the risk of liquid flooding in, care should be taken to prevent vapor ingress through valves that are not tight or through cracks. If appropriate, testing should also be carried out in surrounding spaces. Certain enclosed spaces, such as ballast tanks, are frequently heavily framed, and movement within them can be severely restricted, especially to someone wearing a breathing apparatus or lifeline. Any movement within a confined space should be carefully planned, and great care taken to ensure that personnel do not become wedged or trapped inside. The body will always try to keep its vital organs, the brain, heart, liver and kidneys, at 37 degrees Celsius. As the body warms up, because of work or heat gain from other sources, the brain pushes more blood to the skin surface, increasing its temperature. This switches on the sweating process. If the sweat evaporates, the skin cools, in turn cooling the blood. If the sweat cannot evaporate, the body temperature will progressively rise. The pulse rate will increase, and as the body temperature approaches 40 degrees Celsius, a person will experience nausea, disorientation, and cramps. This is known as heat exhaustion, and, if not corrected, will lead to collapse and unconsciousness. All the above can be made worse if the posture is poor, such as from crouching or bending in low headroom, and the work task involves heavy physical effort. If heat exhaustion is a risk, then frequent breaks should be taken, replacement fluids supplied, and arrangements made to rotate the workers inside the space. Most enclosed spaces do not have lighting inside. Consideration should be given to providing personnel entering such a space with adequate illumination, suitable for safe movement and the task to be performed. The impact of noise may be increased within a confined space. If a pump is running in a compartment above or adjacent to a work site, provision will have to be made for hearing protection of those involved. Although quality has improved greatly, it is still common to find that radio communication between those inside an enclosed space and those outside is difficult. If personnel are deep inside a double-bottom tank, for example, the distance, the intervening steelwork, and the noise from any machinery running nearby may be a barrier to reception. Large, open cargo spaces tend to generate echoes, making radio transmission difficult to understand. Personnel wearing breathing apparatus will find it difficult to use portable radios. Many breathing apparatus sets today have integral microphones, which do make communication much easier, and because it is one less piece of equipment to carry and operate, they are much safer. It may be that entry into an enclosed or confined space has to take place during heavy weather and in rough seas, in order, for example, to check for suspected damage, although such measures are considered drastic and should only be undertaken in emergencies. Equipment or cargo may have broken free and pose a significant additional hazard to those entering, as would the free surface effect of any liquid sloshing about in the bottom of the space. The impact on or from other operations underway at the time should be considered in the risk assessment, and, if identified as a potential hazard, those operations should be suspended while entry is taking place. A practical example of this is that many terminals will not connect any cargo hoses until all tank inspection is completed. Similarly, it is a safe, practical approach to suspend all ballast operations if entry into a ballast tank is taking place, simply to eliminate the possibility of the wrong valve being operated in error. If applicable, the special nature of a proposed task, the peculiar structure of the enclosed space, any specialized testing procedures, and any other factors pertaining to the intended operation should be considered when planning the entry. In summary, the risk assessment for entry into an enclosed or confined space should include evaluation of the following potential or existing hazards: the possibility of a dangerous atmosphere being present or arising subsequently in the space, the present and previous contents of the space, the condition of the space, the means of access into the space, the nature of the proposed task in the space, the contents or condition of adjacent or connected spaces, restrictions on free movement resulting from the size and structure of the space, the work location and nature increasing the possibility of heat exhaustion, the effect of poor illumination, any limitations on communications, the impact of weather, sea state, etc. on the operation, constraints on and resulting from any other operations going on at the time, and any other relevant influences and factors. The standard steps in any risk assessment are: 1. Identification of the hazards. 2. Assessment of the risks associated with those hazards, that is, those persons at risk of harm and that material, equipment or area of the environment at risk of damage. 3. Application of controls to eliminate or reduce those risks deemed unacceptable by evaluation of existing controls and the application of additional measures. 4. Documentation of findings and actions. 5. Monitoring and adjustment. Many of the hazards associated with entry into an enclosed or confined space can be effectively eliminated or safely controlled by good operating and safety practice. This incident occurred on a tweened-deck dry cargo vessel which was fitted with several deep tanks designed for the carriage of vegetable oil cargoes. She was on a return run to Europe, having called at various small island ports in the South Pacific, where she had loaded palm oil in several of the deep tanks. Access trunks led from the main deck on each side between number 1 and number 2 hatches to lobbies at tween-deck level. In each lobby, there was a bolted manhole cover at the top of the appropriate deep tank. The deep tanks were protectively coated and fitted with stainless steel heating coils to maintain the cargo temperature during the voyage and to raise it prior to discharge. The palm oil was discharged in Hull, England, and the tanks were subsequently ballasted with seawater for the next passage to the South Pacific. No cleaning was done after the discharge of the palm oil, and the ballast was loaded directly on top of the remaining palm oil residue. Some 10 to 12 days into the voyage, a crewman was taking routine tank soundings when he noticed a bad smell emanating from the sounding pipes for number 2 and number 3 deep tanks. This was not unusual and regarded as a normal feature of the carriage of ballast water in these tanks, but he did report the matter to the chief officer. Following company requirements, the ballast water was changed after passing through the Panama Canal. Deballasting commenced during the afternoon of the 2nd of October. During the evening watch the same day, the 2 engineer cadets were sent forward by the second engineer to check on the water levels in number 2 and number 3 tanks, as the ballast pump had lost suction. The cadets first checked number 2 tank by going down the access trunk to the tween deck level and opening a steel screw-down inspection port in the manhole lid. Having established that the ballast seemed to be out, they re-emerged and opened the door of the access trunk to number 3 tank and the pump room. Here they found a foul smell of such strength that they decided it was unsafe to enter and reported back to the second engineer. On the assumption that all the ballast water was out, both tanks were reballasted with clean seawater. After reballasting, however, the smell from the air pipes of both tanks did not improve. A fleet circular from the company drew attention to the possible dangers of hydrogen sulfide gas evolving from decomposing palm oil in ballast water, and requesting masters to ensure that ballast water is changed at sea, and that under no circumstances was access to the tanks or pump rooms to be allowed until entry procedures had been followed and an entry permit issued. The circular had reportedly been discussed on board at a recent safety meeting, but this had not been minuted. A number of tanks were emptied and cleaned as the passage progressed. On the morning of the 21st of October, the chief officer asked the second engineer to pump the ballast out of number 2 and number 3 tanks. 2 seamen were instructed to remove the lids from the tanks in the tween deck lobbies. At about 0700 hours, the Bangladeshi deck sarang reported to the bridge to discuss the work for that day. The chief officer anticipated that the 2 tanks would be empty by early afternoon and discussed preparations for tank cleaning with the sarang. There was evidently some confusion, however, and it is possible that the deck sarang had misunderstood when the tanks would actually be empty. When they turned to at 0800 hours, the deck sarang went forward with 5 men to the tank access trunks. They rigged a hose and prepared a cargo cluster light. The deck sarang and 1 seaman went down the access trunk at the starboard side leading to the tween deck lobby, where the manhole access to number 3 deep tank had been opened earlier. The deck sarang entered the tank. Almost immediately, the seaman at the manhole shouted up the access trunk, "Sarang fall down!" He then entered the tank himself, and the other men on deck heard him calling, "Sarang! Sarang!" from inside the tank. Then it went quiet. At around 0850 hours, the third officer on watch on the bridge heard shouting on the deck. At the same time, another seaman alerted the chief officer, and he ran forward. He issued instructions for self-contained breathing apparatus to be brought from the safety locker. Without waiting for it to arrive, however, he also entered the trunk. He was wearing a boiler suit, but no self-contained breathing apparatus, and had not stopped to put boots on. A seaman also went in, but only got a little way and came back out on deck due to the strong smell of gas. A few moments later, the master arrived, closely followed by a seaman bringing a self-contained breathing apparatus. The master donned the breathing apparatus and descended to the tween deck level, where he found the hose and cargo cluster which had been rigged earlier. He saw the chief officer slumped on a stringer plate below the manhole, but could not see the others. He considered that he was unable to assist on his own, and returned to the deck. The chief engineer and second engineer had now arrived on the scene, and also donned self-contained breathing apparatus sets. They entered and descended with an emergency oxygen supply. They located the chief officer and started to administer the oxygen. As the chief engineer lifted the chief officer to a more upright position, he noticed another man hanging upside down from the stringer plate with one leg caught in the ladder, later identified as the serang. A stretcher was lowered, but put aside by the two engineers as being ineffective in the circumstances. Shortly after this, a self-contained breathing apparatus low-level alarm sounded, but the two engineers were unable to identify which set it was coming from. They decided it was safest for both of them to exit, and by the time they reached the deck, both alarms were sounding. Spare bottles had been organized by the master, and the chief engineer, this time accompanied by the second officer, returned inside wearing fresh sets. The second engineer went to get still more cylinders. The chief engineer took a line with him that was rigged through a block at the top of the access trunk. He attached it to the chief officer, and an attempt was made by those on deck to lift him out. The line, intended for lowering tools, was not strong enough and parted, the chief officer falling back down and landing on a stringer plate. The chief engineer secured the line a second time, but then had to exit the space due to a low-level alarm sounding on his second set of bottles. A third fresh supply was provided, and the chief engineer again returned to the bottom of the trunk. This time he took a lifeline with him and secured that as well. The chief officer was eventually lifted out onto deck at around 1000 hours. Resuscitation and cardiac massage were attempted by the master and purser, but were abandoned when it became apparent that there was no sign of life. As there was no chance of the deck serang or the seaman inside the tank being alive, the master decided not to risk further personnel, and ordered that deballasting should continue with a view to recovering the other bodies when the tank was empty. The mixture of palm oil residues and salt water had led to the generation of hydrogen sulfide gas and corresponding oxygen depletion within the deep tank and in the vicinity of the tween-deck lobby after removal of the manhole lid, which claimed the lives of the chief officer, the deck serang, and the seaman.